Hello everyone, let's continue with the rest part of this slides. So basically we already mentioned about for single layer perceptron we can perform the training like this way. So we use this method, okay, just based on the digitive. So we want to back propagate the arrow according to this digitive, and then we use this method to adjust weight. Okay, so this alpha is the learning rate. Okay, and then this is just arrow you can calculate. This is the input for the JS node. This is the digitive of the activation function, and then after you calculate the digitive of activation function, you already know the in, right? You calculate the in just combining all of the input by weighting, right? By weighting. So you just insert the variable, the x means the x variable to be this in value. Okay, so that means all of them can be calculated easily. Okay, so let's look at for example, we do an experiment, compare the performance with another traditional learning algorithm, DTL's decision tree learning method. And then we look at two problems. The first problem called the majority on 11 inputs. Okay, that means the majority, they will just find the majority among 11 inputs and then provide what is the result, true or false. And then the second one is for the restaurant data. So this one, the basic idea is that for example, if you want to go to a restaurant to have your dinner, but it will have a lot of vectors that will affect your decision. So whether you will go or not, you will have a lot of this. For example, the weather, the traffic, waiting time, the price, and so on. That means whether you will have dinner in that restaurant based on a lot of vectors. And then in the chapter 20, we use this example to explain decision tree. We can draw a decision tree. For example, today is raining, I will not go. Today is shiny, we'll go. Okay, and then next one, the traffic is high, we'll go, or not, or what's the chance to go, and then so on. So that means you will have a decision tree, and then each decision will also attach a probability. That means it's not 100%. Right? Even today is shiny, you may not go. So that means each decision has a chance, and then it will depend on a lot of vectors. So we compare with the data method and then show the result. You can find if it's single layer perceptrons, the red one, its performance sometimes is better. This is, of course, higher is better. Okay? So this is the training set size. If it's larger size, the performance is increasing, and the decision tree also increase, but not in this range, not increasing much, almost remain stable. This one increasing a little bit. This one seems no, almost remain unchanged. Also cannot outperform this decision tree method. So that means it sometimes it may be better, like this majority. Sometimes maybe not better. That's why I also mentioned in the past. So we can only we could only afford shallow. We call it shallow layer neural networks, because we don't have a lot of data. Like this data is not good. The size is not big. The other one is the training is slow, and we don't have good training algorithms and capacity for in the computational power. Okay, so that means even though it was proposed just right after World War II, but after 70 years, more than 70 years, it is not that successful. Okay? Only recently, for example, we can say it's around 2012. Okay? We mentioned the lec11 just raised attention from the academics and the industrials as well. So everybody is using deep learning now. Okay, so that means we found deep learning really can outperform other traditional methods, like I mentioned, decision tree or the support vector machines. Before deep learning, people use support vector machines for a lot of cases. Okay, this is just want to mention only single layer perceptron is not powerful enough. Okay, this is the conclusion we want to have here. And then that's why we want to talk about multi-layer perceptrons. Usually we talk about this is like a neural network, though we mentioned is still perceptron, but it's multi-layer neural networks. So for easy to do the deduction, because later we also need to deduct the training algorithm for multiple layers. Single layer seems easy because you only have one layer. Right? One layer, just you need to adjust the weight in this one. That's easy. Okay, based on the arrow, adjust this weight. That's already done. But multiple layer, right? You need to consider more. So this is output, this is input. There's arrow here. You can adjust this one, but how about this one? Correct? So these weights, Wji, Wkj, all of them need to be adjusted. How to propagate the arrows from the end layer to the first layer? Correct? First layer. So this is so it's not so hard if you already understand the single layer perceptron training algorithm. Correct? So in fact the idea is the same. Okay, we build on top of that one. Okay, let's look at this one. The input we use AK, so you can find out we use IJK. I is the output layer, J is the hidden layer, and here we said this is input. Input, you can think about this as first layer. They receive the input, maybe your input is here, but you receive the input in this layer, and after that connect with the next layer and this one. Okay, so the weights between the K and this one. So this one there's no weights. For example, this one is already sent. This one must be input here. This one another input here. There's no input which connect with a lot of others. So for previous one, that's just because we have this difference. We cannot say okay this one only send to one neural. Correct? We need to. This is just a part of the feature factor, so it must connect with multiple neurons. Maybe it's not all, but the unit is not only one. So this is the difference. But here we just use a layer to accept inputs. So this is first subfactor, second subfactor, third, and continue. So all the input just in this sequence, okay, accept neurons, accept the inputs, and then connect with the hidden layer. Hidden layer, that means not input, not output. All the layers in between input layer and output layer we call the hidden layers, and then each one you call the hidden neurons or hidden units. Okay, let's look at this one. How can we develop a training algorithm to adjust the weights during the training? Okay, let's look at. So we want to look at its expressiveness, that means its capacity. In the past, we know for only single layer it can represent maybe just only just for example will be good for some problem, maybe not good for all the problems. And the single layer one is only represented like this half, kind of like one side of the cliff, cannot represent the other side. Okay, like this surface. But if it's multi-layer, we can represent like this one. So it's like a cliff have two sides. We can represent both. Okay. So it can represent all continuous functions with two layers, and then we can represent all functions, that means either continuous or non-continuous function with three layers. That's great, cut. So you can find it here. Just like this is a continuous one example. So it's two inputs, okay, and then this is another one. So you can find here why this one is like a cliff, the other one is like a bump, cat. This is not the same. So how can we get this? How can we get this one? Okay, so we can find if we can represent this one, if we combine two opposite facing threshold functions, we can make a ridge. Okay, this is one, this is the other one. So opposite facing threshold function. So one is, for example, just the activation function. One is sigmoid in this way. The other one maybe is in this way, cut. So we can represent, and then we represent both sides. So you can find this activation function. So the activation function still have very important impact on the final shape, cut, because that's the threshold. This is like sigmoid, okay. And then if we combine two, okay, if two perpendicular ridges, this one ridge, another one, if they have another one which is perpendicular to this one, then we can make a bump. Okay, so that means they will be enhanced in the middle, and then others we have this impact. Okay, just change it quickly, correct? Because they are perpendicular to each other. So one is up, the other is down. So this panel will be dropped quickly. Okay. And if we add bumps of various sizes and locations to fit any surface, we can use bumps different size, different location. We can fit any surface, complicated surface, cut. Because the unit surface seems like some part is bumping, sometimes it going bumping. If in the other side will be the valley, cut, go inside. So either bumps, then still bumps, cut. Okay. So the proof requires explosion in many hidden units. So for example, you can refer to the decision tree layer proof. Okay, we don't need to have a clear understanding of this one, but just have this knowledge that will be enough. Okay, and then next, the most important, how to train. Right? We know it's powerful, but how to train this multi-layer perceptron? In fact, we still based on the previous one to get this. Okay. So the previous one, you can find that we use this method. Okay, this method. It seems like the derivative is important. Okay, derivative is always like this way. If it's arrow backpropagated, the preferred weight is minus arrow, and then the activation function derivative, and then use the in to calculate the value, and then the xj is the input of that neural j to the current neural. So neural j to the current neural, xj arrow for this the expect output, cat, and the obtained output, the estimate output, the difference is the arrow. So that means we can always calculate like this way, cat, arrow. So you can think about. Okay, so for this one, we can use that method to adjust this weight, this weight, this weight, this weight, and then you can also calculate in a similar way to calculate the weight adjustment for here. But now the issue is that how can you find the arrow here, okay? The arrow here, because you don't know what is the expected. Okay? This one already know the expectation is y. You got a y hat, but what's the expectation for here? You don't know. If you don't know of course you don't know what is the error. You don't know the expected one. You know the output. Output is the AJ cut, so the AJ. But what's the output? What's the expected output? So in fact, for this one, we follow this rule. You know this one, there's a weight cut, weight, and then we back propagate the error for this neuron. Because this you can find this one is connected with multiple neurons here. So we define the error according to the weights, and back propagate the error according to the weights. Okay, the weights connected. So that means if it's a strong connection between the two neurons, we have more adjustment, more errors back propagate to this one. If less connection, less strength between this one, so it will occupy less error propagated to here. So this is the basic idea. If we know the error, and then you can keep doing cut, because you just need to think about this is like a single layer. You know the error and back propagate based on this function cut. Okay, so based on this one, and then use this one to adjust. So you know the error, you know the activation function, you know the IJ cut. So this is the idea. Let's look at the okay, the mass. Okay, so called back propagation. In short, it's called BP. BP training. Even currently, the deep learning. This is we talk about the shallow cut. It's like shallow. We haven't covered deep learning. Deep is deep neural networks, but it has some other variations. Later we talk about convolutional neural network, recurrent. But here, even deep neural networks will still follow the same idea, back propagation method. Okay, let's look at the complete back propagation algorithm. So in your project, you may have to implement some step of this algorithm. That's why we spend the time. And then your task is to implement a training algorithm for neural networks. So output layer is same as for the single layer perceptron. Okay, single layer output, that means this one cut is the same as this one. So we don't have much difference. You just use that one to calculate. Okay, because this one you already know what's the expected value, what's the expected output, what you have obtained. Of course, you can just use that one. So it's WJI. Just this one, right? It's WJI, initial WJI plus alpha and alpha j delta I. So here delta I means the arrow, okay, the arrow, and then plus this one. That means this one we represent this one to be delta I. Okay, delta I. Okay, so delta I is this one. Okay, so that means where delta I is arrow I, and then multiplied by the G prime, and then in I. Okay, same as this one. And then the hidden layer, that means this layer. How can we calculate the weights adjustment for this one? Right? This is hidden layer for these weights. This one already adjusted based on that formula. So the back propagated arrow from the output layer, you can find it here. We mentioned the method. Okay, we use based on the weights of the weights, we back propagate. Which one dominates? Which one has higher weight? We will also back propagate more arrows to it. Okay, to that neuron. So delta J is equal to this one, the G prime in J, and then sigma WJI W delta I. So you can find this one is based on the weighted, based on the weight. So it's how much weight we populate to the JI for the j neural. So it's based on the weights w, j, I, j and I, okay, j and I. Sigma, you can find it sigma j I w I. So that means combine all the weights, okay, all the weights related to this wi. That means you have you can find I is here, okay, I is here. So you have multiple, okay, multiple. And then still apply this one. You can find it has similar form, okay, and the g prime in j. So this is just backpropagate according to the weights. Maybe this one cannot see clearly, but later you will find it. And after that, we updated the rules for the weights based in the hidden layer based on this one. Kj, kj is this one. So adjust the kj. We based on, if we got wj, we use the similar idea. We only replace the I to be j. I to be j. Right? And then aj will be ak. Because it's is the input here, right? And for this output. Okay, this neural. This k neural. This is j neural. Okay, I neural. Okay, this is k neural, k and j connected. This is j and I connected. So you can find this is exactly the same as this one. And then this w data j, this part is just based on the distribution kind of among the weights. So though the most neuroscientists deny that backpropagation occurs in the brain, but we still just have this formula like this way, okay, like this one. So that means it works, because though we don't have that backpropagation, we first go through the model, go through our brain, and then find the error, and then we backpropagate. We train a new neural. So, but this is what we can do based on our current structure. We need to calculate, right? We need to update the weights. So our human brain, even till now, we don't have enough understanding on it. Okay. So the backpropagation derivative will be like derivation. Okay, derivation. That means we want to show the process why it will be like that way. So you can find it, we can continue, right? Next one we can continue similar way. So continue. So this is the formula. Let's look at how to get that formula. So the arrow is this one. This one we know. This is the yi is the ground truth. AI is the output. So it's the output. That means the estimated one. This is the ground truth, the expected one. This is arrow. And then if we do the derivative for this layer, where the sum is over the nodes in the output layer. Sum. So that means this is all the arrows. Okay, you need to measure all the arrows in the last layer. So sum all the arrows together. Sum all of them. And then if we do the derivative, run the E, run the WJI, correct? JI, that means the hidden layer, correct? Next, the layer just in front of the output layer. This one, correct? JI. So you want to adjust this one first, and then adjust this one. Okay. So do same thing as before, correct? So this one is 2 times, and then cancel out the 2, and then this one will perform the run for this digit, run the JI for this one. YI to itself is a constant, so that means only AI contains WJI, correct? Because it combine the input and then do an activation function and get output. So you have a minus, correct? So that means this function first do like f square, and then 2 times f prime, So 2 times cancel out of 2, and then f prime, this one 2 to the prime, this one is a constant, this is -1, and then -1 here, and then do this one again. So this f also have a g, right? So we want to do the derivative around the g, around the x. So this is x, this is g, and then we expand it, right? AI, we already know what is the AI. Okay, AI is g in I, the input of a neural I. Okay, and then after that activation function, and then we further, this one is a function, right? Is g, and then we perform the g prime, and then we do the inside g, like you have f, g, and h, and the h function do the derivative for this x. Okay, and then we get this one, and then we expand this in I is why we do that, because it haven't show up the wji. We want to expand the in I to get the wji, then we can cancel out the unrelated terms, only keep the last keep the one which is related to wji, to the x. All of others no response, no impact. So we sigma wji aj, this is based on the equation we mentioned before. So that's the input to the j's node, to the j's to the ith node. So all the node connect to this one, ji, and then combine by the weights. So ji, aj, I is fixed, So this one you can find only the wji, aj, that term. When j is equal to j, j is equal to j, will be the one related to this one. All other terms, if it's 0, j minus 1, j plus 1, there's no impact. Okay? So this one will be easy. We can still calculate this one. So that one will be just cancel out this one, like the ax. Okay? You get only the aj remaining. So that's why it's like this way. Keep this one, so this one get the result is only aj, and then aj, if we rewrite, we mentioned aj, this is minus ij, and this part is data I. Okay, data I, we noted as data I is yi minus ai is arrow, and then it's derivative. Okay, so data I, in fact, in the past, so here in multi-layer we use data I. In the single layer, we give a new name to it called arrow. Okay, not arrow. Okay. Anyway, just like it's a combination of arrow and then derivative of activation function put in the value with in the value of derivative of activation function with in. Okay, this is for this one. That means we already calculate the derivative for the hidden layer, to adjust the hidden weights between hidden layer and the output layer. And then we can continue. For example, after we got this one, so next one we want to calculate, this is the, we know the ratio, how to change the arrow. We can put alpha, then we know the learning rate. But after you got this one, you also need to adjust the wkj. So next one is calculate for the k, how to adjust k. So that will be this one. Run the e, its own arrow, and then run the kj. So it's similar. So like the previous one. So only difference is like the variable, independent variable will be changed. Previous is x, now maybe it's t. So like this one, kj, and then similarly like the previous one. You have these things, so you can just go through this one. In fact, it's not hard to get this one, but finally we want to mention you get a similar form as this one, minus ak data j, okay. So that means you can find we can propagate the arrow. We can propagate the arrows from the end, okay, from the output layer to the hidden layer, calculate its weight in between, and then next one aj, you can find aj data I, and here ak data j. So that means we only change is the output, okay, and then data j, data k. So it's arrow, and then multiply by this one, this portion, okay, arrow multiplied by this one. Okay. So that means we also can adjust the weight for this one. Right? How to propagate the arrow? We mentioned just based on weights. We do the distribution. Okay, that will be here, just like this one. Use this function. Okay, weighted. Okay. So that means for this arrow, we combine all the arrows, all the arrows based on the weights. You can find it like this way. That's why I mentioned, because I is only for, currently we only show one AI, but we have multiple neurons, so they connected with this one. If there's no connection, means the weight is 0. So that means we combine the arrows according to this weight. Combine the arrows. You can see it arrows, relate to arrow, and then of course you need to use the derivative. The arrows cannot backpropagate directly because you applied the derivative, get the arrow, and then if you go back, you need to do the derivative. You first do the activation, and then if you want to go back, you do the derivative. That's the reason. But you backpropagate the arrow according to the weights. You combine multiple source arrows from multiple sources, multiple output neurons. Okay. So that means that you can continue and then backpropagate and continue. You can calculate. Okay, just following this method. This is the backpropagation approach. Okay. Okay, let's continue for the next. So the backpropagation learning, you can find at each epoch we sum gradient updates. We mentioned this before. Each epoch will contain a list of examples. Each example, after perform this one, you get the arrow, and then you can calculate the weight for each of the weight. Each adjustment for each weight. But you have to sum all the gradient update together and then do a single round. So that means wait till you finish all the training, all the samples. You do adjustments at the same time, by summing all of the gradient updates. And then after that, maybe some may be added, some may be increased, because for you maybe it's too much, for that one maybe too few. So sometimes we need to increase, sometimes we decrease. So we consider all of the increases, and then together that will be the good estimation value to adjust the weights. And then that means for all examples and apply. This is one epoch, means one round. You finish all the samples in this round. So here we set the training curve for 100 restaurant examples. Find the exact fit for this one. So 100. This number of epochs. That means we perform this round of training. Each time is feeding 100 examples. That means your data set has 100 data. Okay, 100 data points. And then this is the total error of a training set. You can find that with the more number of epochs, with the number of epochs increasing, the total error will be decreasing. Right? That means it's converge. It's converging to a local to a global optimal. So typical problem is that later we'll also, if we cannot cover this one, for example for the CNN training, we may share you. I think I will share you the training card, the last 12 lecture 12 slides, the reference slides. We show that means unit will have an overfitting issue and have underfitting issue. So overfitting, if you find that this arrow dropped, almost remain unchanged, but you still keep doing the overfitting we mentioned before, okay? That will be overfitting. And then next fitting is that you stop too early. You stop here. It's still decreasing, so you need to wait till it converges. Means the arrow remain almost unchanged. Right at the beginning of that trend, you stop. Do not perform too many, because if you perform more, that will be overfitting, correct? So you need to find the correct location to stop the search. That one will correspond to a model, because this, if it remain unchanged, even the loss or the arrow here remain unchanged, but the weights are still updating. So that means it will just increase the accuracy by a little bit, but change the arrow, change the weights by a lot, maybe. That will be just fit the training data, but has less power in generalization in the testing data. So we want to avoid that case. Okay. So next one, we compare again. Okay? We still talk about that restaurant problem. Decision tree is red one. We change. Okay? Now the green one is this one. You can find now that it catch up. Okay? If you get more data, it may have the same performance, even better performance than the DLT, decision tree method. So multi-layer perceptrons are quite good for complex pattern recognition tasks, because it can represent nonlinear function. So that's why it will demonstrate its power or capacity in dealing with those complicated problems. If for simple problem, maybe don't show much difference. But just resulting the hypothesis cannot be understood easily. This means even you got the model perform well, but you don't know how to explain this model to others. This also till now is also a problem. So sometimes we can get a better performance, much better performance, but just because of it do a lot of nonlinear transformation. You know, we have activation function which is nonlinear, and then another activation function. So in the end, you have very complicated nonlinear function for the y equal to fx. So you don't know how to explain this model to others. So this is still the current challenging task waiting for you to explore. Okay. And then let's look at its performance on other related applications. Later we'll also talk about this type of question again, but here just mention about NN does improve the state of art by a lot. For example, like this handwritten digit recognition, you can find here. Use the k-nearest label, kn, we got a 2.4% error. If we use the multi-layer perceptrons, 400, 310, this means 400 is for the input layer. So this image is 20 by 20, so in total you have 400 pixels. And then hidden layer have 300 neurons, and the output layer is 10. You must have 10, correct? Because you have 10 digits. So the output layer just indicate how many categories, how many digits. So each one, what's the probability? You will give a value based on the multi-layer perceptron based classification. This one dropped the error to be 1.6 error. But if we use lec11 is in front of lec11, even simple, but it's have more layers. You can find we have this one, correct? So this one we keep the image, make it bigger, so it's 768. For here, we just reduce the downsampling. So 20 by 20, but here is what result is 20, 30, 20 something cut. 20 something by 20 something. Anyway, you can calculate. And then hidden layer we have 2 layers, and the output is still 1 layer. So the error will be dropped to 0.9%. And then current best, this one of course is long time ago current best. Now the performance is even better than this one. So for example, with this is color machines, vision machine. So now we already mentioned kind of AnexNet or something. They can drop this performance to even further, make it maybe 0.223 or something. So that means 98% it will be accurate. Okay. So this one have very great potential in the, for example, like checks, right? Which is positive checks with handwritten. So in fact, most I think maybe all of the checks had, most maybe 99% of checks have been processed by machine learning algorithm, handwritten digit recognition algorithm, not manually processed by human. Okay. And then this is last slide to conclude right at time, right? So basically for this chapter we talk about the concept about what is neural networks. It is a simulator of human brain, but it's not in a biological way. We simulate in a function level way, right? At the function level. So most brains have lots of neurons. Each neuron is like a linear threshold unit. Of course, this is like a we want to approximate this one. That's why we use activation function. And then we talk about different type of neural networks. The first one is perceptrons, just only 1 layer. Okay, but it's insufficiently expressive. We already know it's not powerful enough. Sometimes doing well, sometimes not. And that's why we have the multi-layer networks. So both perceptrons and multi-layer network, they follow the same training algorithm called BP, back propagation algorithms. So we utilize this BP method to derive the BP algorithm for multi-layer networks training. It is sufficiently expressive, but it's harder to train. So that's why we developed that BP algorithm. It can be trained by gradient descent. Okay, that one is called gradient descent just because we backpropagate the arrows based on the gradient, based on the weights, and then the gradient is just that derivative. We call it derivative is the gradient. Right? So in fact, this is called a gradient descent training algorithm, GDS. Okay, and then it has many applications. We mentioned speech, driving, handwriting, fraud detection. Okay, it can be used in everywhere. I think we use learning and engineering, cognitive modeling, neural system modeling, and so on. Right? Okay, the subfield have largely diverged. And each one will use different type of neural networks. For the natural language processing, we need to use recurrent because we need to remember the previous word and then combine with the next word. We form a phrase and then remember phrase. We get a sentence. And then we understand meaning. You cannot identify each separate word. That's why it's called a long short-term memory, LSTM. So that's long short-term memory network. It's very powerful in natural language processing. Okay, and then this one we already finished the introduction about neural networks. So next week we'll continue with the I think it's deep learning. We'll continue with the. Okay, we maybe initially introduced this reference a little bit, so we will not cover this one in detail. just introduce why. This one is very important paper, just because these are the three big guys in this field. They contribute to the training algorithms, a new deep learning framework, and also these three guys joined the industry. For example, this is in Facebook, this one in Facebook, this one in Facebook, this one in Google, and so on. That means anyway, in that three companies. Later we'll talk about. I think. Okay, Facebook, right? Google, correct? Google, hint. Okay, maybe still now, even till now, they're still in this one. This maybe Google in Canada. This one is Facebook. I think in USA, maybe should be, yes. So we'll talk about this one, and then next one we'll talk about CNN, convolutional neural networks. Just this is also another very important part. We'll cover this one in detail. Then that's the arrangement, and then that's all. Okay, and then I will right away just finish the next one. We'll post the PA3, the third project, very soon. Okay, just continue. For example, deep neural networks. This is to handle the visual information processing. Okay, it will be still deep learning, but it will involve a convolution. Convolution just want to extract features, make the image smaller and smaller, the feature image. Okay, it can be used to do the feature object detection and so on. So this one will be covered in the next week. Okay, I haven't finalized whether I will just ask you to implement the CNN or just only pure DNN method, deep learning method. Okay, let's see. Okay, see you next week.